Alright, so this lesson is going to focus on how to use matrix equations to decompose rational equations into parts. So we're going to talk more about what that means, but first of all, I want you to go ahead and try this warm-up. You will have a homework assignment tonight, which will be partial fraction decomposition. You are only doing numbers 2, 4, and 6 for homework, so please make sure you get that written in your agenda book. So if you want to go ahead and pause this video so you can give you a couple minutes to work on this warm-up, and then we're going to go over it. Alright, so you are supposed to, in this warm-up, circle all of the terms that contain an x squared. So if you see here, our ax squared contains an x squared, and there's nothing else in this expression that contains an x squared, so we're not going to be circling anything else. We're now going to box all the terms that have an x. So this positive 5ax has an x in it, this positive bx has an x in it, and then this positive cx has an x in it. And then finally we're going to put a triangle around those other terms that do not. So basically that's all the ones that are left. And so these are our terms that have nothing else, either an x or an x in them. So we would just call them basically a constant term. So that's going to help us today when we are decomposing rational equations into parts. So if you think about things that decompose, what do you think about? So you should be thinking about things that break apart, which is exactly what we're going to be doing with rational equations and expressions, okay? I don't know how many of you remember this because it was a long, long time ago, but we did do adding and subtracting rational equations, okay? So we're going to get there in just a sec. We are going to go ahead and check your homework from last night, which is again using matrices to fit 3 points. Here are my 3 points, point 1, point 2, point 3, into basically a quadratic equation, and that's a really bad arrow. So we used basically 3 points to fit them into a quadratic. Okay, so for this first one, for number 1, here's the answer for number 1. So your little a would have been -1, your little b would have been -2, and your little b would be 5. So the equation would actually be y equals -1x squared, and then -2x plus 5. Okay, so you could just replace all of those a, b's, and c's for each of these problems, and you would be able to see the function that fits those. If you remember, what we did in this lesson is basically we took the x value and squared it to get our first column. So we took -2 squared to get 4, -1 squared to get 1, and 3 squared to get 9. And then we just took the actual x values in the second column, and then we had basically that magic column of 1s. Okay? We took the inverse of that and then multiplied it by a column matrix of our y values. Okay, so this is kind of the long and short of what you did, and then when you did that, you would have gotten the result of basically these 3 points. So for number 1, you would have got -1, -2, and 5. So you could repeat that process with all of these, and you would be able to get the equation that would contain these 3 points that were given to you. Okay? Alright, so today's lesson, decomposing. So, you should have a note sheet in front of you. So, do you remember? That's the question. Do you remember how to subtract 2 fractions that contained an expression basically as a denominator? So, if I wanted to get a common denominator for both of these fractions, this one has an x and this one has an x minus 1. So if you remember, we kind of, please don't actually say this, cross-multiplied, which is finding a common denominator. So we looked over here and we saw that this denominator was x, so we multiplied this fraction by x over x. We saw that this fraction had an x minus 1, so we multiplied this by x minus 1 over x minus 1. And then we simplified. So our common denominator is actually just one copy of x times x minus 1. Okay, you only write your denominator one time. So if I get a common denominator, my common denominator is x times x minus 1. And it's basically the 2 expressions that are in the denominator. So x and x minus 1. Now I'm going to take and distribute that negative 4 to the x and to the negative 1. Remember, that's this negative 4 being distributed to this expression. And then I just did 1 times x, or negative 1 times x, which is negative x, so that's how I get this one here. And after I distribute, I will be left with negative 4x plus 4 minus x. And then I'm going to distribute on the bottom as well, so x times x and x times negative 1. And then finally, I am going to combine the like terms. So if you see I have an x and an x, so that means I'm going to do negative 4x, so I'm going to take this whole term, and I'm going to subtract x, which that will give me negative 5x. So my final expression, when I subtract this fraction minus this fraction, will give me negative 5x plus 4 over x squared minus x. So this is something that we did all the way back in like October. Okay, so I know that's a long time ago. Okay, but that we did do it, even if you don't remember it. This is one process that we did. Okay, now, what are we doing today? So today, we are working backwards. Okay, so we are taking that expression of negative 5x plus 4 over x squared minus x, and we are working backwards to basically get this right there. Okay, so we are now trying to decompose, or to break apart, this fraction right here into two separate fractions. Okay, that's what we're doing. We're breaking apart basically a complex fraction. Okay, so I'm going to warn you, there's a lot of algebra involved in this. Okay, so I want to make sure that you're following me. We're going to do several examples, basically 3 examples today. We're doing 1, 3, and 5 on the back of that sheet. You will probably not have enough room on that to finish out, especially number 5. So you may want to think about having out a journal or something like that if you want to just take some extra notes. Okay? So let's start with number 1, and this is number 1 on the back of your worksheet. It's also a slide that you see on the note sheet, so it's in both. But basically number 1 is the problem we just talked about. Okay, so if I had negative 5x plus 4 over x squared minus x, I want to break it apart into 2 fractions. And the reason why I know it's going to be 2 fractions is if you look at my numerator, this is a 5x. It has a degree of 1, right? Power of 1 right here. And then I have a 4. So this is kind of like that, what we talked about yesterday, the ax plus b. So I'm only going to have an a and a b when I break this apart. So don't let that confuse you, though. There's lots of a's and b's, and I just want to make sure that you're not confused by that. Okay? Now, this piece up here is what we will always give you. So please don't think that you need to know how to get this piece up here, because this is what's going to be given to you. Okay? We're going to tell you basically this part right here. But if you're wondering where that comes from, that basically comes from factoring the denominator. So if I take x squared minus x and I pull out an x, this is going to factor into x times x minus 1. Okay? So that's where I get the x and the x minus 1. But you're going to be given that. You're not going to expect it to have to factor that. Alright. So the first thing that we're going to do is we are going to multiply through by the denominator. So you might be going, well, what does that mean? Okay, well, that means I'm going to take this right here, and I'm going to multiply it here, here, and here. Okay, so I'm multiplying it through the entire equation. So I'm taking the denominator, I'm multiplying it through. Well, if I have this expression in both the numerator and the denominator, it's going to cancel out. So all I'm going to be left with is negative 5x plus 4, which is basically the numerator of the original expression that I was given. Now, if I do it up here, if I multiply x times x minus 1, notice there is already an x on the bottom of that fraction. So what's going to happen to this x and this x? Well, they're going to cancel, and I'm only going to be left with an x minus 1 in the denominator. Okay? Finally, with the b, again, I'm going to multiply through, and again, what do you think is going to happen if I take this x times x minus 1 and multiply it here? Well, basically what's going to happen is that's going to cancel the x minus 1s, and all I'm going to be left with is an x. Okay? So the first thing I do is I just multiply through by that numerator. Some students see this as kind of that cross multiplication process like we talked about in that first example. It's not really called cross multiplication, so don't call it that. It's multiplying through by the denominator. Alright, so what do you see different between the expression here? Let me erase this. What do you see different between this expression right here and then this expression? So getting from here to here, what do you see different? So you should see that we distribute the a to the x and the minus 1. So basically what I'm doing is I am distributing the a to the expression x minus 1 and the b to the x. So that's going to leave me with ax minus a plus bx. Now this is what we did for warm-up. How did we go from here to here? Well, this is where we grouped the like terms. So I took the ax and the bx, I grouped them together, and then I factored out an x. So this step here was to rearrange terms and factor. Which I forgot that word. Okay, so this is rearranging terms and factoring. Alright, so that must mean that a plus b equals negative 5 and negative a equals 4. Now you might be going, where in the world did you get that from? Well, I'm going to show you. Okay, first off, here's my x right here. Oops, let me switch to my highlighter. Okay, so here's my x. I'm going to get a different color. Actually, let me just clear my annotations off the screen, and then I can take away the color a little bit. Okay, so here's my x. You notice there's an x here too. What do you see as the coefficient of x here? Okay, my coefficient is negative 5. What do you see as what's with the x over here? There's an a plus b. So that means a plus b equals negative 5 because they're both with the x on both sides of the equation. So I'm going to say a plus b equals 5. Alright, now, for here, 4 is by itself. Well, negative a is by itself over here. Okay? So that means that negative a equals 4. Now, a lot of students want to right away jump into doing, I'm going to scratch these out because I don't want all the a's and b's to confuse you. You can scratch them out on your paper too. Okay? A lot of students want to use substitution to solve this. So they're going to say, well, a equals negative 4. If I plug that back in, then that means that b equals 1. Well, you're right. That is true. Or excuse me, b equals negative 1. You're right about that. But again, remember we're focusing on solving these with matrices because that's the unit that we're in. So this is 1a, and this is 1b, and this is negative 1a, and there's no b here. So my coefficient matrix is 1, 1, negative 1, and there's no b in the second equation, so I call that 0. Now if you remember to solve a system, I do the coefficient matrix inverse times negative 5, 4, which is these values here, and that's going to give me my solutions, which in this case are for a, negative 4, and for b, negative 1. So now all I do is I take that back up to the top, and I plug it back in. So I take this a, which is negative 4, and I plug it in for the a up here. And then I also take the negative 1 here, and I plug it in for b. So there's the negative 1, and I just plugged it in for b. So I literally took what I started with. Now that I have a and b, I can fill it in, and I now know if I decompose this complex fraction, or basically this rational fraction, that I will get two individual fractions of negative 4x minus 1 over x minus 1. Okay? Alright, so there's another video. I think this one's rounding out to about 15 minutes. So I'm going to stop this video, and there's another one that we're going to play, and I'm going to do examples 2 and example 3.